This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is reactive impedance. Our objective is to quickly discuss why reactive elements like capacitors and inductors present impedance to AC sources. We'll discuss why current leads or lags voltage for reactive elements and how frequency and component value influence current magnitude. This lecture operates under the presumption that viewers watch the capacitive complex impedance, the inductive complex impedance, and AC Ohm's Law lectures, all available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. If you're adept in the skills as presented in the aforementioned lectures, you can no doubt easily numerically calculate the complex impedance of a capacitor or an inductor with a given component level value and an excitation frequency. Additionally, you are undoubtedly capable of using AC Ohm's Law to calculate current given voltage and impedance values, or vice versa. The intention of this lecture is to step away from the numbers for a bit and simply consider why reactive elements like capacitors and inductors behave the way they do in AC systems. Sit back, relax, and enjoy the tour. Let's take a look at capacitors first. Recall from our discussions about time-variant DC responsive capacitors that initially uncharged capacitors experience a surge of incoming current, followed by rising voltage. Similarly, a discharging capacitor experiences an initial surge of outgoing current, followed by falling voltage. This behavior can be summarized as current leading voltage for capacitive elements, and that the current spikes occur before a change in voltage. This is essentially the same reason capacitors exhibit a phase shift between voltage and current in AC systems. During the charge phase, current rushes into the capacitor and capacitor voltage rises. During a subsequent discharge phase, current rushes out of the capacitor and capacitor voltage drops. The problem in identifying the present state of a capacitor in AC systems is that the polarity in AC systems cyclically oscillates at a frequency too fast to allow a technician to change the leads of a voltmeter or ammeter to adequately reflect the actual state and polarity of the capacitor. Consider a capacitor in an AC system with an ammeter and voltmeter in the following locations. The ammeter is oriented in to out, left to right, and the voltmeter is oriented positive to negative, top to bottom. Because we can easily lose ourselves in semantics, just think of voltage in terms of absolute magnitude, i.e. forget the sign. If voltage absolute magnitude is increasing, the capacitor is charging. If voltage absolute magnitude is decreasing, the capacitor is discharging. Let's take a look at a full cycle of an AC waveform in quarter cycle increments. The first quarter cycle is characterized by rising voltage. This capacitor is charging. The next quarter cycle is characterized by falling voltage. This capacitor is discharging. The next quarter cycle is characterized by increasing voltage magnitude. This capacitor is again charging. Finally, the last quarter cycle is characterized by decreasing voltage magnitude. This capacitor is discharging. The first half of the cycle is easy to explain. The initially uncharged capacitor at first experiences a large surge of positive or incoming current. As capacitor voltage rises, current decreases in magnitude and then stops altogether when the capacitor reaches full charge. The fully charged capacitor then starts to discharge. As capacitor voltage drops, the capacitor experiences negative or outgoing current. Here's an important switchover. Once a capacitor fully discharges in one direction, it seamlessly transitions to another charge cycle, only this time in the opposite direction. Pay attention to the orientation of the ammeter in to out, left to right, and the voltmeter positive to negative, up to down. The uncharged capacitor experiences a large surge of incoming counterclockwise current. Given the orientation of this ammeter, this will be considered negative current. Capacitor voltage rises, and given the orientation of the voltmeter, this will be considered negative voltage. The fully charged capacitor then starts to discharge. As capacitor voltage drops, the capacitor experiences outgoing current. Given the orientation of the ammeter, this will be considered positive current. Capacitor voltage drops and the cycle begins anew. Before we move on, allow me to briefly discuss the concept of power. I know we haven't explored AC power yet in its full complexity. However, consider this very basic understanding that quite like DC power, that instantaneous power is a product of instantaneous voltage and instantaneous current. The first quarter cycle is characterized by a period of positive voltage and positive current. Positive times positive is positive, meaning the first charge phase is an expenditure of positive power. This means the supply is delivering power to the capacitor, and the capacitor is storing this accumulation of energy in an electrostatic field. The second quarter cycle is characterized by a period of positive voltage and negative current. Positive times negative is negative, meaning the discharge is an expenditure of negative power. What is negative power? If positive power is defined as the source delivering power to the capacitor, one might define negative power as the capacitor returning that accumulation of stored energy back to the source. In a perfectly efficient system, all energy stored in the previous charge phase would be returned to the source during the subsequent discharge. In the real world, however, we might expect there to be losses in the system. However, for today's purposes, let's consider this a mathematically perfect entity unbound by the constraints of reality. The charge process was a period of positive power and energy storage. The subsequent discharge was a period of negative power and energy return. There is an equal and opposite exchange, and in the end, no real work was done. However, current did flow from the source to the load and back again. This type of positive and negative exchange of power is called a reactive interchange, something we'll explore at length in later lectures. The second half of the cycle is a repeat of the first half, only in the opposite direction. The next quarter cycle is characterized by a period of negative voltage and negative current. Negative times negative is positive, meaning this charge is an expenditure of positive power. Supply is again delivering power to the capacitor for 1/4 of a cycle, and the capacitor is storing this accumulation of energy in an electrostatic field. Finally, the last quarter cycle is characterized by a period of negative voltage and positive current. Negative times positive is negative, meaning the second discharge is again an expenditure of negative power. As previously, negative power means the capacitor returns the previously stored energy to the source. A single cycle of sinusoidal AC therefore consists of 2 complete charge and discharge cycles, 2 bursts of positive power, and 2 equal and opposite returns of negative power. Long story short, current leads voltage for capacitive elements because a change in current must precede a change in voltage as the capacitor stores and releases energy in its associated electrostatic field. I say again, current leads voltage for capacitive elements. This is why a purely capacitive element always experiences a current waveform 90 degrees in advance of the voltage waveform when calculated using phasor equivalence. For example, given a 15 microfarad capacitor at an excitation frequency of 60 Hz, this capacitor presents a complex impedance of roughly 176.8 ohms at an angle of negative 90 degrees. Let's say this capacitor is known to experience a voltage differential of 50 volts at an angle of negative 15 degrees. I am absolutely confident that any manipulation of Ohm's law will demonstrate current will lead voltage by a relative 90 degrees. Current should therefore have a phase shift of 90 minus 15 degrees or positive 75 degrees. An application of AC Ohm's law, solving for current, where current is voltage over impedance, demonstrates we should anticipate this capacitor will draw roughly 282.7 milliamperes at an angle of positive 75 degrees, consistent with our expectations. One can use this fact as a means of checking your work. If you get a phase shift between voltage and current of anything other than 90 degrees, it means you are doing it wrong and you need to revisit your work. Now that we've got a general understanding of why current and voltage are out of phase with one another for capacitive elements, let's discuss how capacitive component magnitude and frequency influence impedance and thus current. Your base understanding of Ohm's law demonstrates that given constant voltage, low impedance elements will draw large amounts of current, whereas high impedance elements will draw small amounts of current. This should be well within your capacity to understand on a very instinctive level. You'll additionally recall that the magnitude of capacitive complex impedance is 1 over 2 pi times the frequency times the capacitance value. You'll note frequency and capacitance are in the denominator of the complex impedance formula. The influence of these two properties can be most efficiently illustrated using graph of capacitive complex impedance as a function of frequency. Given constant capacitance, small frequencies result in large capacitive impedance magnitude. Conversely, given constant capacitance, large frequencies result in small capacitive impedance magnitude. Frequency is the rate of polarity oscillation. Lower frequencies correspond to slowly changing waveforms, where 0 Hz, or no change, represents DC. Capacitors at low frequencies present large impedance. Think about it. What's the steady state impedance level of a capacitor in a DC system? After the transient charge phase ends, a capacitor essentially appears like an open circuit or an infinite impedance. After a capacitor is fully charged or fully discharged, current flow ceases. The complete halt of current flow perfectly defines a high impedance element. This makes sense. Above DC or 0 Hz, slowly oscillating waveforms present slowly changing voltage. As a result, the charge or discharge process doesn't have an incentive for a massive exchange of current, i.e. current is low at low frequencies, synonymous with a high impedance element. This lack of incentive to charge or discharge results in sluggish, low magnitude exchanges of current. Conversely, at high frequencies, quickly oscillating waveforms present rapidly changing voltage. As a result, the capacitor has a high incentive to rapidly charge or discharge, resulting in massive exchanges of current, i.e. current is high at high frequencies, synonymous with a low impedance element. If you think about it, capacitors in high-frequency systems are always in the early stages of a charge or a discharge, synonymous with a high burst of current. Now that we've got an understanding of how frequency affects impedance, let's discuss how capacitance component magnitude influences impedance. Capacitance is in the denominator of the capacitive complex impedance formula. Given constant frequency, high capacitive elements present low impedance, whereas low capacitive elements present high impedance. This is a reflection of capacitor construction. Large capacitors are physically larger and have a lot of room for charge. As such, they draw a large amount of current. This is synonymous with a low impedance element. Conversely, smaller capacitors are physically smaller and don't have a lot of room for charge. As a result, they draw less current, synonymous with high impedance elements. All right, that about wraps it up for capacitors. We learned why current leads voltage or capacitive elements and how frequency capacitance influence impedance. Let's do the same thing for inductors. It's really more of the same, except we're dealing with magnetic fields instead of electrostatic fields, lagging current instead of leading current, and impedance magnitude that increases as a function of frequency and component value instead of decreases. If you want to think about it this way, inductors are the opposite of capacitors and vice versa. You recall inductors in DC systems experience an expanding magnetic field, which creates an oppositional voltage surge. The oppositional voltage surge initially chokes current and then fades over time as current increases. Energy is stored in the inductor's magnetic field. During the release stage, the inductor's magnetic field collapses. The collapsing magnetic field generates a transient voltage pulse that temporarily continues to push current in the same direction and then fades over time. Any energy stored in the collapsing magnetic field is released. This behavior can be summarized as voltage leading current for inductive elements, and that the voltage spike occurs before a change in current. Importantly, by saying voltage leads current for inductive elements, I am also directly implying that current lags voltage for inductive elements. These statements are equivalent, although I tend to prefer the second variation. It can be said current lags voltage for inductive elements. This is essentially the same reason inductors exhibit a phase shift between voltage and current in AC systems. During the storage phase, the oppositional voltage spike initially chokes current, and during the release phase, the voltage spike momentarily continues to push current in the same direction. As with capacitors, the problem in identifying the present state of an inductor in an AC system is that the polarity in AC systems cyclically oscillate at a frequency too fast to allow a technician to change the leads of an ammeter or voltmeter to adequately reflect the actual state and polarity of the inductor. Additionally, inductors might seem to suffer from a causality paradox, which I hope to resolve in a moment. Consider an inductor in an AC system with an ammeter and voltmeter in the following locations. The ammeter is oriented in to out, left to right, and the voltmeter is oriented positive to negative, top to bottom. As previously, let's take a look at a full cycle of an AC waveform in quarter cycle increments. One might be tempted to begin our analysis here at time t equals 0, and then divide the waveform into quarters as follows. However, let's try a different approach. Remember that AC waveforms are cyclical and repetitive. It really doesn't matter when or where we begin our analysis. I suggest we start here, where current is equal to 0. This choice of start point prevents the causality paradox I alluded to earlier. If we begin our analysis at any other time, the inductor already has some existing magnetic field. However, if we begin here, the inductor is empty and carrying no current and has no existing magnetic field. In short, it's best to start the analysis at an empty state. Again, it's important to remind ourselves that instantaneous power is a product of instantaneous voltage and instantaneous current. The first quarter cycle is characterized by an initially high oppositional voltage, which falls as current rises. This is a period of positive voltage and positive current. Positive times positive is positive, meaning the storage phase is an expenditure of positive power. The supply is delivering power to the inductor for a quarter of a cycle. The inductor is storing this accumulation of energy in a magnetic field. An important switchover occurs when the inductor releases the stored energy during the next quarter of a cycle. As the magnetic field collapses, a voltage surge, oriented positive to negative bottom to top, occurs such that the current continues to travel in the clockwise or positive direction. Given the orientation of the voltmeter, this will be considered a negative voltage. Current drops and eventually crosses zero. This second quarter of a cycle is characterized by a period of negative voltage and positive current. Positive times negative is negative, meaning the release phase is an expenditure of negative power. As previously, negative power means the inductor returned the previously stored energy to the source. In a perfectly efficient system, all energy stored in the previous storage phase would be returned to the source during the subsequent release. In the real world, however, we might expect there to be losses in this system. However, for today's purposes, let's again consider this a mathematically perfect entity unbound by the constraints of reality. The storage phase was a period of positive power and energy storage. The subsequent release phase was a period of negative power and energy return. There's an equal and opposite exchange, and in the end, no real work was done. However, current did flow from the source to the load and back again. This type of positive and negative exchange of power is called a reactive interchange, something we'll explore at length in later lectures. The third quarter of a cycle is characterized by a period of negative voltage and negative current. Negative times negative is positive, meaning this is another expenditure of positive power. The supply, again, is delivering power to the inductor, and the inductor is storing this accumulation of energy in an expanding magnetic field. Finally, during the last quarter cycle, as the magnetic field collapses, a voltage surge oriented positive to negative, top to bottom, occurs, since the current continues to travel in the counterclockwise or negative direction. Current drops and eventually crosses zero. We're right back to where we started, having completed one full cycle. The last quarter of cycle is characterized by a period of positive voltage and negative current. Negative times positive is negative, meaning the release phase is an expenditure of negative power. As previously, negative power means the inductor returns the previously stored energy to the source. A single cycle of sinusoidal AC therefore consists of two complete storage and release phases, two bursts of positive power, and two equal and opposite returns of negative power. Current lags voltage for inductive elements because a voltage change precedes a change in current as the inductor stores and releases energy in its associated magnetic field. I say again, current lags voltage for inductive elements. This is why a purely inductive element always experiences a current waveform 90 degrees behind the voltage waveform when calculated using phasor equivalence. For example, given a 120 millihenry inductor at an excitation frequency of 400 Hz, this inductor would present a complex impedance of roughly 301.6 ohms at an angle of 90 degrees. This inductor is known to experience a voltage differential of, let's say, 60 volts at an angle of positive 20 degrees. I am absolutely confident that any manipulation of Ohm's law will demonstrate current will lag voltage by 90 degrees. Current, therefore, should have a phase shift of 20 minus 90 or minus 70 degrees. An application of AC Ohm's law, solving for current, where current is voltage over impedance, demonstrates we should anticipate this inductor will draw roughly 198.9 milliamperes at an angle of negative 70 degrees, consistent with our expectations. One can use this fact as a means of checking your work. If you get a phase shift between current and voltage of anything other than negative 90 degrees for purely inductive elements, you are doing it wrong. I should note real-world inductive elements normally feature a small amount of internal resistance that can be taken in series with the inductive portion, and as such, don't truly exhibit a 90-degree lag between voltage and current, but rather something less, in the order of negative 88 degrees to negative 85 degrees for well-constructed inductors, or even negative 75 degrees or less for inductors built in third-world sweatshops from old coat hangers, hot glue, and tin cans. The larger the internal resistance, the less the lag. Now that we've got a general understanding of why current lags voltage for inductive elements, let's discuss how inductive component magnitude and frequency influence impedance. Your basic understanding of Ohm's law demonstrates that given constant voltage, low impedance elements draw large amounts of current, whereas high impedance elements draw small amounts of current. This should be well within your capacity to understand on an instinctive level. You'll additionally recall that the magnitude of inductive impedance is 2 pi FL. You'll note frequency and inductance directly influence inductive complex impedance magnitude formula. Graphically, one can demonstrate the influence of these two properties using a graph of inductive impedance as a function of frequency. Given constant inductance, small frequencies result in small inductive impedance. Conversely, given constant inductance, large frequencies result in large inductive impedance. Given constant frequency, a smaller inductor presents a lower impedance, whereas a larger inductor presents a higher impedance. Since we're discussing two different properties, frequency and inductance, let's discuss each one independently, beginning with frequency. Frequency is the rate of polarity oscillation. Lower frequencies correspond to slowly changing waveforms, where 0 Hz, or no change, represents DC. Inductors at low frequencies present low impedance. Think about it. What's the steady-state impedance of an inductor in a DC circuit? After the transient storage phase ends, an inductor appears as a short circuit or 0 ohm impedance. After an inductor contains a stable magnetic field, it experiences no voltage differential. This perfectly defines a low impedance element. It makes sense. Above 0 Hz, slowly oscillating or low frequency waveforms present slowly changing current. As a result, the magnetic field in the inductor isn't rapidly expanding or contracting, and the inductor does little, if anything, to moderate it. This lack of opposition will result in high magnitude exchanges of current. Conversely, at high frequencies, quickly oscillating waveforms make the magnetic field rapidly expand and contract, resulting in high oppositional voltage spikes, keeping current at a smaller, more manageable level, i.e. current is lower at high frequencies, synonymous with high impedance elements. If you think about it, inductors in high-frequency systems are always in the early stages of a storage or release, synonymous with larger bursts of oppositional voltage. Now that we've got an understanding of how frequency affects impedance magnitude, let's discuss how impedance level influences impedance magnitude. Inductance in units of henries directly affects inductive impedance magnitude. This is a reflection of inductor construction. Smaller inductors don't have a lot of coils, or they don't have a core capable of concentrating the magnetic field. As a result, induced oppositional voltage effects aren't noticeable, synonymous with high magnitude exchanges of current, whereas larger inductors have a lot of tightly wound coils and might be filled with some exotic material that unusually concentrates the magnetic field. As a result, induced oppositional voltage effects are very noticeable, synonymous with low magnitude exchanges of current. All right, that about wraps it up for inductors. We learned why current lags voltage for inductive elements, and how frequency and inductive component magnitude influence impedance for inductors. Let's finish this lecture with a quick summary of what we learned by comparing and contrasting capacitors and inductors in AC systems. Current leads voltage for capacitive elements because a capacitor undergoes two back-to-back charge and discharges for a single cycle of AC, one in one direction, another in the other. During a charge, the capacitor consumes power. During a discharge, a capacitor supplies or returns power. A full cycle of AC therefore results in two equal and opposite exchanges of positive and negative power. Capacitors present high impedance and draw low current at low frequencies. Conversely, capacitors present low impedances and draw high current at high frequencies. This is a reflection of how frequency influences the length of the charge in the discharge phase. Slower charges and discharges necessarily result in lesser exchanges of current. More rapid charges and discharges necessarily result in greater exchanges of current. Large capacitors present low impedance and draw high current. Conversely, small capacitors present high impedance and draw low current. This is a reflection of capacitor construction, i.e. a measure of its ability to store charge. Essentially, the opposite can be said of inductors. Current lags voltage for inductive elements because inductors undergo two back-to-back storage and releases for one full cycle of AC, one in one direction and a second in the other. During a storage phase, the inductor consumes power. During a release, an inductor supplies or returns power. A full cycle of AC therefore results in two equal and opposite exchanges of positive and negative power. Inductors present low impedance and draw high current at low frequencies. Conversely, Inductors present high impedance and draw low current at high frequencies. This is a reflection of how frequency influences the expansion or collapsing of the magnetic field. Slower frequencies result in a slower changing magnetic field, thus lesser oppositional voltage and more current. Conversely, more rapid frequencies result in a more rapidly changing magnetic field and greater oppositional voltage and less current. Small inductors present low impedance and draw high current. Conversely, large inductors present high impedance and draw low current at high frequencies. This is a reflection of inductor construction, i.e., a measure of its ability to oppose changes in current. That is that. In conclusion, this lecture examined impedance experienced by reactive elements like capacitors and inductors at a conceptual level. We discussed why there exists a phase shift between voltage and current for reactive elements and how frequency and component magnitude influence reactive impedance. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. I'll see you again during the next lecture of our series. And remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.